Hi, welcome to our Capstone presentation. We'd like to give a short introduction of our background. My name is Wanda. I graduated with a double major in finance and natural science from NYC. I spent the last 4.5 years at two banks, JP Morgan and Citigroup, and since then I've been eager to transition to data science, which is an evolving field.
My name is Ho Fai Wong. I graduated from French school, actually, Télécom Paris, majoring in networking and computer science. And I've been a consultant at PricewaterhouseCoopers over the last 8 years. I'm a manager in IT infrastructure, and we use elements of data science. I wanted to hone in on my data science skills, and hence why I came to this bootcamp.
Hi, I'm Radhey Shyam. I did my PhD in physics from Clemson, and after that I did like 2 years of research in physics and try to learn the data science. Then I think, no, I have to get a formal training. That's why I joined the NYC Data Science Academy, and here I am.
Hello everyone, I'm Joseph Wang, and I graduated from UT Austin Physics Department from Theoretical Physics. And after that, had my 6 years of academic research experience at Georgetown University and Los Alamos National Lab for material research. And then I joined Chevron for 1 year for oil industry research on acoustic physics application. And right now I'm making a transition to data science this year. That's why I'm here.
So thanks again for coming here and spending your evening with us. We'd like to kickstart our presentation. So our team is called Anomalous, and we decided to study network intrusions. So many of you today probably come from a variety of backgrounds, from different organizations. It might be an academic institution, it might be a financial institution, or whatnot. In any case, your organization likely has a dedicated team to prevent network intrusions, to protect your internal data and your client-facing websites from attackers, from people wanting to hack into your network, to steal your customer data, steal your passwords. Recognizing this challenge, we wanted to build a predictive model capable of distinguishing between safe and malicious connections, while balancing model accuracy with interpretability and computational power. So our data set is actually sourced from MIT's Lincoln Laboratory. They were funded by the government to research this case study. They simulated a typical US Air Force situation where they peppered a local area network with many attacks, and they fall into 4 different categories. One is denial of service attacks. You probably hear a lot about these in the news but don't recognize them as DOS or DDoS attacks. Basically, what happens is hackers overwhelm your client host with a variety of attacks seeking to crash your website. One famous case of this was back in 2011. You might have heard of the hacktivist group called Anonymous. They crashed PayPal when they refused to process transactions aimed at supporting WikiLeaks. So that's one type of attack category. The second one was remote to local. The third one is user to root, and the fourth one is probing. About the data, there are 41 features for these connections that we were studying. One connection is basically a TCP packet going from source to client. We had a training set and a testing set. The training data had about 46.5 malicious connections versus about 53 normal connections. Instead of classifying every single type of attack, which there is a wide variety, we only looked at normal connections and abnormal ones. And the type of data included binary types, nominal, and continuous. As a high-level overview, they fall into 3 different categories, one being basic features of individual TCP connections, content features within a connection suggested by domain knowledge, so having an understanding of networking, partitioned the data in a certain way. And additionally, traffic features that were computed during a 2-second window when the LAN was peppered with these attacks.
Thanks, Wanda. So I'll get started into a little bit of the basic exploratory data analysis, right, before we get into actual predictive modeling. So first off, we looked at the distribution of connections by protocol type. So for those who aren't very familiar with network protocols, these are the communication standards, protocols, that define how different servers, networks, users, enterprises communicate with each other over internal networks, over the internet. Some of the most popular and common internet protocols are TCP, UDP, and ICMP. So TCP, you might have heard of it. HTTP, browsing the web, runs on TCP. So does FTP, file transfer, SMTP for email, and so on and so forth. So you can see that the largest number of connections falls under the TCP category because it's a type of protocol that can allow for error connection, reliability over the network, and so on and so forth. Within those connections, there's about an equal distribution of normal connections versus malicious connections. All right, so that's good to notice. Followed up with UDP, User Datagram Protocol, so smaller number of connections. Now, for those who aren't familiar, once again, and I apologize, I do have to go through some of the networking jargon for the rest of the presentation to make sense in the context of a network intrusion detection case study. So UDP is a protocol that's used in situations where you don't necessarily need to have reliability and error management for your packages. All you need is low latency, right? You just need to have a package be sent and recognized and whatnot. So UDP, you might have heard of DNS, DHCP, they run off of UDP, right? So in those cases, majority of the connections are normal. And lastly, ICMP, so Internet Control Management Protocol, the large majority of those connections are actually malicious. So even if you may not have heard of ICMP, you may have heard of ping, right? When you're trying to ping a website, just a quick hit, see if I can hit that website. Is that website up and available? That's on ICMP. So you can imagine how that might be useful for a potential attacker, for denial of service attacks or distributed denial of service attacks. It's an easy way to hit a website. So that was interesting to see the distribution already based on these protocols. Another of the categorical variables that we had was, I apologize, it's kind of cut off here with the paper, but the flag, the connection flag. So each connection, a TCP connection, has a flag, which basically indicates the status of the connection at that point in time, right? So imagine you're initiating a conversation with another person. First of all, you have a handshake. You need to make sure that you're talking to the right person. You need to make sure the person knows that person is actually talking to me. Make sure that there's authentication and whatnot. So there's a whole process of back and forth of handshake and whatnot, and they're captured by these flags. So I won't go into too much detail on these flags, but just the highlights. So the first one, SF, that indicates that the connection and the synchronization was established and ended normally, right? So if you can see, the most number of connections correspond to the SF flag, and the majority of them are normal. Connection ended normally, odds are it was not an attack. But though there are still some attacks that kind of use that type of flag. The next is S0. You can't really see that, but it's S0. That's essentially a flag that indicates a connection was established or requested, but there was never a response back. So I'm basically an attacker trying to initiate a conversation with an enterprise. They never respond back. That would be an S0. So you can see that the number of malicious connections greatly outshines the number of normal connections. And it goes on and on. Reject, reset. These are essentially flags that indicate that a connection was rejected, like the name suggests. So odds are malicious. Or reset. Once again, odds are malicious. So looking at it from an exploratory perspective, kind of makes sense. And lastly, we want to look at another categorical variable, which was the service. So I talked a lot about the protocols, TCP, UDP, ICMP, but these are just, if you will, communication languages, right? What's the actual service being provided? So from the top, you can see, for example, HTTP, right? Web service, HTTP, that's what you see in your regular browser when you go on a website. So the most number of connections corresponds to HTTP, understandably. A large part of them are normal, some are malicious. The next one, private. Private services. I would imagine that's what an attacker would want to hit in an enterprise. A lot of malicious connections, and so on and so forth. So I won't go through all of these, clearly, but you do see a very long tail of connections that fall within the malicious category, all right, with a very low number of connections, but they still are there. So that's something that our algorithm will have to be able to detect. But having a low number of connections doesn't necessarily mean it's malicious. You can see you've got POP3, which is email, and some MTT, which is network time protocols for so there are some services that have a fewer number of connections, but that are normal. We can't just assign as malicious. Okay. So I want to continue the exploratory analysis by looking at some of the features, the variables that we had in our data set. This is a variable factor map. So what I did was I applied principal component analysis to my feature space, trying to figure out what were the primary components, the main directions in the feature space that covered the most variance in the data set. I just depicted the features within the space of dimension 1 and dimension 2, right, just for visualization purposes. And what you can see is that the features, the closer they are, the more correlated they are, if you will. The closer they are, the more meaning they have. So the first grouping, these are features which relate to the TCP rejection error. We have features here which are related to within a 2-second window, right, of this connection, what's the rate of connections that are hitting the same servers, but for different services. Different services to the same servers within 2 seconds. Interesting. These are features related to the number of connections for the same hosts. So for the same host, over 2 seconds, how many different connections hit those servers? Here are features along this dimension which relate to synchronization errors. So I mentioned the handshakes earlier. So these relate to handshakes, errors with the handshakes. Right? And lastly, connections to same services for same hosts. So just looking at a high level at the original features projected onto this 2-dimensional space, I kind of feel like the dimension 1 probably relates to synchronization errors versus dimension 2, which probably relates to rejection errors. So after this, we kind of have a sense of the continuous variables and what they mean, and the categorical variables from the previous slide, what they might also indicate with regards to normal versus malicious connections.
Sure. So we ran a k-means clustering algorithm to partition the data into 3 different clusters that were very interesting to look at. So the first cluster, as you see in red, has Neptune as the highest, and normal and IPC coming in second. So Neptune is actually a DOS attack, and the IP sweep, Satin, and port sweep are actually probing attacks. So what does this mean for an organization? What is the trade-off between network security and network reliability? Well, as you can see here, when you have this type of attack pattern coming into your server, it might be easy to distinguish, oh, Neptune is a DOS attack, we can kill it. However, you're also killing a good portion of normal connections. So you might be cutting off important business that day. So for the risk-averse organization, that may not be a desired situation. The second cluster in green is very easy to notice. It's mostly concentrated, it's 100% concentrated in Neptune. So this attack pattern is easy to identify. It's great for our intrusion detection system. Finally, the third cluster, which is mostly concentrated in normal and has a sort of tail with the other attacks you see here. So yes, it's easy to identify normal connections. However, the smaller distribution in these other probing attacks and DOS attacks are malicious, and it might be one of those attacks that kills your entire client base for your month or so. So there's really a give and take between network security and network reliability.
Mm-hmm. Absolutely. Thanks, Wanda. So we did some exploratory analysis to kind of understand our data, what we had to work with. Now on to the predictive modeling. Right? So we want to start off with logistic regression, since it's a classification problem, and not only that, but with a Lasso penalty. So essentially what that does is it tries to bring some of the coefficients to 0 to reduce the number of variables that we have in our final model. So the first graph here on the top left indicates the misclassification error by lambda. So as you can see, the minimum lambda was all the way on the left, which kind of retained 110 features, but we wanted to balance interpretability with accuracy. So instead of choosing that value, we chose log lambda of -3 to retain only 12 features, right? More manageable, and for an enterprise, it's less data to collect. And with network traffic, there are millions and millions of bytes per second. We need to reduce the feature space. So with that selection of lambda, which is the regularization parameter, here on the top right, we depicted the training error at the top and the testing error here at the bottom in red. The vertical line here indicates, once again, the lambda value -3, which selected 12 features. So we have roughly 95% accuracy in train, but a much, much lower accuracy in test, 70%. So straight off the bat, something's off. You can see here it drops down because of overfitting. But straight off the bat, either something's wrong with our model or there's something we haven't figured out in the test data, or training data for that matter. So we looked at some of the features, the 12 features that were retained by our Lasso penalty regularization. And so looking through these, they kind of make sense, right? So ICMP, we talked about that earlier. That's a protocol used by ping, for example, that's typically used in a lot of attacks. Makes sense that it has a high coefficient. Private services, typically the target of network attacks, right? The count, a lot of connections to the same server over 2 seconds, probably an attack. On the flip side, SF, if you recall, that's the TCP flag for a connection that ended normally. So odds are that's a normal connection, and so on and so forth. So looking at the coefficients of the retained variables, the model seemed to make sense. So to summarize, right, 95% accuracy in train, 70% accuracy in test. And the true positive rate was only 49%. So once again, why is there such a large discrepancy in our train versus test accuracy? Is there a problem in the model I built? Simple though it may be. Or is there something more in the test data, right? So what I tried to do was to shuffle my train and test data. We were lucky enough that our test data also had the outcome response labels. So I took the train data, the test data, combined it, shuffled it, randomly sampled, and split it into a new train and test set. Right? And I reran my same approach, my logistic regression with Lasso penalty. Using the same 70-30% split, tenfold cross-validation, same value of lambda. In this situation, I actually picked 11 variables. The coefficients here that you can see, similar to what I had before, still made sense, right? ICMP, private, and on the flip side, SF. But my accuracy is a lot more in alignment now. 92% accuracy in train, 86% accuracy in test. A lot more in alignment. Still a difference because of obviously train versus test data. So shuffling the data aligned my test and training accuracy. Right? Is there an underlying bias in the test data? Or is my algorithm still insufficient in some way? So I wanted to try other algorithms first. I'll go quickly through this, but I tried naive Bayes, Laplace coefficient of 1, cross-validation, and so on and so forth. In my unshuffled scenario on the left here, I still have quite a discrepancy between my train and test accuracy. Once I shuffle my data, they're pretty much in alignment. Right? So 2 algorithms that kind of highlighted the same observation. And as I was doing this for these 2 algorithms, my colleague was running the same type of analysis on tree-based algorithms.
Hi. That's when we decided let's switch to tree-based algorithms, because as we know, random forest makes a pretty good prediction. So that's why I think next algorithm to try was the random forest. And as you can see from the parameters, mtry is the number of the parameters we are selecting. So we are selecting 15 parameters out of 120 parameters. And how it becomes from 41 to 140, because there was a service. If you remember from the earlier, there was a service factor. So service has a 70 levels. So random forest cannot handle more than 32 levels. So we split the 32 70 factors into 1 and 0. We dummify this thing. So that's why now I'm selecting the 15 factors out of 15 variables out of the whole 121, and this is the number of the trees. So we run out of the bag, we run the random forest, other parameters were the default setting, and we run and we got the really good training error. This is the out of bag error. So it means we run the algorithm on the training set, and whatever is remaining from the training set, that's out of bag, and we test the model on that one. So it's a really good one. But when we test the accuracy, same thing. So accuracy was 77%, which is not good. So, and we say, and also the true positive was 62%, and this was really low. So I also tried the same technique. We shuffle the data and let me try. So it means something is not good between this test data. So I did the same thing. I tried the same algorithm with the same parameters on the shuffle data. Here we can say, see train out of bag error is on the same order. Here we see, yes, accuracy jumps to 99.7 parameter, 99.7%. So same thing. So it means there is something going on with our test data and the train data. So maybe they are not from the same population, or something is going on. So then I decided to run more. This is the variable plot. As we can see, the variance importance plot. So most of the variables are same except these top two bottoms from the earlier plots. So this is the source byte, this is the destination bytes, and they are arranged in terms of their importance based on the decrease in the Gini index. So this is for the shuffle data. It means after shuffling, training and testing, and this is for this one. They looks like quite similar. So there is no change in the importance plot right here. So then we decided to try the Adaboost, which is one of the most commonly used nowadays. So it's the winner of the Kaggle, and it's a variety of the boosting algorithms. XG stands for extreme gradient boosting algorithm. So we keep the learning rate, which is ETA at 0.02, maximum depth of the tree at 5, and run on the training set. Very good prediction power. So when we run on this one, the same story, 76 prediction. So it means something is wrong with our training and test data. After shuffling, when we keep the same parameters, we can see that training accuracy and test accuracy jumps to 99%. So it's a really good prediction if we after shuffling the data. And the next algorithm to try was Adaboost. This is also one of the famous right now. So many Kaggle winners use this algorithm. So ADA stands for adaptive boosting. So what is it's a kind of boosting. You make a tree, whatever error you make, you try to minimize that error. And in ADA boosting, there is a boosting and also a penalty term. So you try to minimize the errors on the previous step and keep on adding the steps. So we use the shrinking parameter, which is a default one, just to test the algorithm. Iterations 50, training error was really good one, same prediction error on this type Cairo side of 78%. If I use the same parameters on this train and test data, we see a completely different story. It means there is something is different between our data. So maybe they are not from the same population or something else. So yes, that's when we decided to do some analysis.
Thanks, Radhey. So as my colleague and I were working in parallel using different sets of algorithms, we observed the same thing happening between train and test. So we figured, okay, if this is happening for all our algorithms, might as well go back to the original data and see what's what. So if you recall what Wanda said in the beginning, that we were interested in detecting if connections were malicious or not, right? We actually abstracted a feature, which was the type of attack, right? So we turned that into a binary variable. So to go back and figure out what was the discrepancy, we went back to that actual variable. And what we noticed was that the attacks didn't have the same distribution between the training and the test data set. There were 2 attacks in train, there were 9 tests, and more interestingly, 17 network attack types that were in test and not in train. Right? So we were running all our algorithms in train, expecting them to perform the same way on the same distribution of attacks and tests. That was not the case. And it makes sense, right? In hindsight, we're working on a network intrusion detection algorithm. Hackers aren't going to stay behind waiting for us to catch up. They're always going to be attacking enterprises with new type of attacks that we don't have in our dictionary or catalog of attack patterns. So shuffling our data, right, and getting a better accuracy is a flawed approach in this scenario. Right? So what you can see here in this diagram here is just a visual depiction of what I just mentioned, which is different distribution of attacks between the train and test set. So the green bars are the proportion of the attacks in the training data set, yellow in the testing data set. Every single yellow bar here that you see that's not accompanied by a green bar, that's a new attack. You see a couple of green bars that don't have an associated yellow bar, okay, those are attacks that were in train 9 test. Less of an impact to what we found. But if you look at 15 and 17, even for attacks or connection types that do appear in both, they might have a different distribution in each data set, right? So all this to say that our approach of discarding the unshuffled data and shuffling and try to get a better accuracy, that's not going to fly. We need to stick with the unshuffled data because that's the very nature of this exercise. Anomaly detection for network intrusions. So with that in mind, we figured, all right, we need to find a different approach to try to give us a better accuracy.
Right. So basically, this approach is called principal component classifier. The idea is basically you learn about, in the training set, only learn about the connection that's normal. And then you look at, if there's a new observation, see how far away from the normal pattern. If it's very far away, right, you characterize some distance to say, oh, it's far away enough. Then you say it's an anomaly and it's an abnormal connection. So that basically is described by this classifier. Basically just means, for example, this cloud, right, how far away is characterized by this distance and this distance. And you can see this is also an outlier and characterized by vertical distance. Okay, and that's basically the strategy. And by doing so, we use this algorithm for unshuffling case to get an 80% prediction accuracy, and we get a pretty high true positive rate, 92%, perform much better than the other algorithm. And we still get a moderate false positive rate. So if that's not good enough, we try something else. We actually, because our algorithm only take care of the continuous variable fully, and we still have discrete variable. So we want to get that information back in our training. So what we do is we take the probability distribution from a logistic regression learning, which take into account a discrete variable, and then we put it into a new column or feature into this algorithm to learn. And we find the accuracy increased by 3% and true positive rate or more or less stay the same, but the false positive rate decreased a lot. So that tells us our performance actually is greatly improved. And the shuffling part we don't need to worry about right now. Yeah. So here is the demonstration of the performance across all different models. We see the anomaly-based model PCC perform very well compared to the rest, and with logistic is even better. And naive-based actually is pretty good as well, but the only thing is the false positive rate is pretty high, and those are something we can improve in the future. So basically, our conclusion is in this application for network detection, we shouldn't shuffle the training data and test data. It doesn't make sense to do this kind of practice. And we also notice the anomaly-based approach will perform much better than the traditional conventional machine learning algorithm. And there's still a lot of improvement we can do on top of the principal classifier and the Bay algorithm. Thanks for your attention.